And then I make a convoluted version of my talk. Okay, the title, as you've seen, is quite ambitious, especially one as a, sorry, I have to, I'm normally walking a lot when I'm speaking, so I have to be strict within the radius. So I'm telling you, when you have a quite varied audience, so there will be different degrees of complexity in what I'm going to tell, and actually it will be a very disordered presentation. But I can thank Laura, because I was starting not to have with a brief introduction of what shallow neural networks are, but you did it, so I can go very quickly to this part, and then focus, sorry, to the part that I was supposed to cover. So deep learning, I mean, that's the quite wide topic per se, and with some possibilities towards NIR spectroscopy. So first of all, how deep is our law? Now, how deep is deep? Because actually, there is already quite an uncertainty about how to define deep learning. Is 2 hidden layer deep? Is 3 hidden layer deep, or so? So let's say that conventionally, yes. Of course, no one agrees, but conventionally, we can tell that a network with 2 hidden layers is a deep neural network. I don't know. I personally am not very persuaded about that, but apparently this is what most of the people would agree. But I think that there is a rationale in that. And I will try, as you will see, I put some, not philosophical, but I put some context slide after this one, and then I will just show a couple of architecture and a couple of things that could be useful for using deep neural networks in the context of NIR spectroscopy or spectroscopy in general. But in thinking, what is, with our eyes, I mean, some of us that I know, we are not computer scientists, we are spectroscopists or chemists or scientists or whatever in this context. So what is the advantage for us of a deep neural network over a shallow neural network for our problem? Or what is the characteristics? When I was thinking about that, actually, if we look at neural networks as approximators, so as actually a way just of representing functional mapping, then, well, those of us who have worked a bit on that know that there is something called the universal approximation theorem that tells us that if we put enough neurons in one hidden layer, we can approximate whatever function. So that's probably why we would think that whatever goes after that is deep, because it's actually, we are not focusing on the approximation capability, but in something more. Something more that is actually, So actually, I think that the important or the main characteristics for us, especially for those of us that are not into chemometrics, about what is interesting about deep learning is that deep learning is actually a sort of representation learning. So it's a sort of learning that is aimed at extracting features. So, and if we look at some of the paradigms of the deep learning that I got from like putting all together series of papers about deep learning, is that they are actually explaining learning of deep neural network with language that is a language that we know quite well. So in the first papers about convolutional network, but also about restricted, actually especially about restricted Boltzmann machine, there are many ways terms like latent variables or latent structure that come into play. So actually, we are speaking about the idea of being able to extract underlying latent characteristics from our data in a way that, as Tom was anticipating before, is not, let's say, fixed a priori, but is learned from the data. And of course, we have actual questions that derive from that. Because of course, when we are like when we are speaking about how to represent our data in a way that in some cases is completely unsupervised, in other cases semi-supervised or guided, then when can we can be sure that one representation that we get is better than another? Or, of course, more directly, when we have a data, then how do we practically perform this feature extraction that translates into different network architecture? And then in some cases, of course, how to develop a good objective function to understand when we stop our learning. Now, in this case, this is why I was telling that in a way, when we speak about representational learning, we could be proud that some of our year-long chemometric concepts entered into play with artificial neural networks. So, okay, this I think, since we are already a bit late, we can just skip. I will just keep some of these aspects so that I came back. The idea, and that is also, let's say, explicitly taken by some of the network architecture, is that we can imagine to have underlying factors that generate posterior distribution that we can be used to model the data, and of course that we want to disentangle or recover this underlying factor. And the idea of deepness is an idea that translates to the fact that we extract these features in a hierarchical way. So ideally, from the more abstract to the less abstract, or from the more abstract to the, sorry, for the more essential to the more abstract features, so to a lower level to a higher level of abstraction in the definition of these features. And so what I will be going to do is just to try to give you an example of some network architecture, a couple plus another one, and that could be used for, that are being used especially for dealing with spectroscopic data, and some comments. So I was in some cases doing images, in other I was stealing, because I'm completely not gifted for doing proper representation, and try to give credit as much as possible where I found to where I've been taking the figures and animation. So the first network architecture that I will be discussing is the autoencoder. Autoencoder is something that is very immediate to us, because it's actually a network that learns lower dimensional, in general, lower dimensional representation of our data. So it's a network that in its, let's say, basic configuration has a bottleneck layer in the middle. That is where I do the encoding for the data. So I start with an n-dimensional vector, or even an n by n dimensional image, or n by j dimensional image, and I arrive to extract features. And these features are, in general, lower dimensional. Also because having a lower dimensional feature, for instance here, if I have two neurons in this layer, I am compressing my data into 2 dimensions. It's one of the ways I am ensuring not to have overfitting. Because if I have an undersampled encoding layer, then in a way I can control the degree of overfitting on my data. The idea is that I'm making compression and then I'm making decoding. So the output layer is an approximation of my original data. So I'm doing learning by presenting my data in general with the same output as input. And I am training when I am reaching the minimum reconstruction error, expressed normally as a square L2 norm between the two. So why I am telling that this is something that is familiar for us, because if we don't put nonlinear functions in the hidden neuron, so if we are using like linear functions in the hidden neuron, this is just BCA. So it's something that we are absolutely familiar with. If we put nonlinear activation function, this is a way for doing no linear data compression, so no extracting no linear component. And for instance, I think it was 2006 or 2007, personally, I was using this architecture to develop a nonlinear SIMCA, because then we get the residuals between the reconstruction, so something like a cube, and we have a projection in a component, let's say, nonlinear component space. Of course, this is a basic structure. There are some variants that we can have. In the basic architecture, we use multi-layer perceptor, but we can use convolutional network both as the encoding and the decoding. This is actually something that is also part of most of the GANs that we will be seeing later on. There can be, I told you that normally we have a lower number of hidden neurons in the bottleneck layer than the inputs. So, and this is a way not to, first of all, to achieve data compression, but also not to have overfitting. But actually, there are other kind of autoencoders that are called sparse autoencoders, where you have more hidden unit than inputs, but with the constraint or with the limitation that only some of the hidden units are activated given a specific input to the network. And this sparsity would be induced by hardness. So just take the first K activated neurons, or by softness using a regularization that induces sparseness. Another way of using the autoencoder is a denoising autoencoder. It's a way of having the possibilities of a compression that is robust with respect to noise. So the idea is that you take the input, you add some sort of noise to the input, and we will be seeing that actually this kind of modifying the input is also one of the way we can have data augmentation. That would be the last part of this talk, not using neural networks. So as an alternative to what we will be seeing, so data augmentation using deep learning, alternative would be to have data that are augmented using all these tricks. So setting some of the inputs to 0, or adding noise to the data, or setting some of the input to minimum or maximum values as a way, in this case, to induce robustness in the mapping. Of course, in the other way, it would be to induce, to extend the available data samples in our data sets. Of course, let's say the big part, as also Tom was anticipating, is given by convolutional neural networks. Convolutional neural networks are particularly suited to process data that are some sort of spatial relationship in the form of pixel spatial relationships as an image, of course, but also spectral or profile spatial relationship as in spectra. The idea, I said that I wanted to summarize what are the main issues, in my opinion, or my main features of convolutional neural network. The idea of locality, of having the same filters that act locally on portion of the signal. The fact that these local filters are shared weight across all the signal or image, the possibilities of having a compression of the information through pooling, and of course, the fact of having many layers to progressively extract the different features. So this we can just skip it because Tom was anticipating, and of course we have some idea. The convolutional concept, of course, as also, I think it was very nice having Tom's part before, because it was giving more a part of the conceptual and philosophical interpretation and comment before the neural network part. Here also I take this image from here I couldn't find the source, where was it? But the thing is that we don't need a neural network for having signal convolution. And in some case, we can define a convolutional filter based on the idea of enhancing specific features in our signal. So this is an example that I take with different possibilities, where I can design a convolutional filter, in this case a 3x3 convolutional filter, just with the aim of doing specific or extracting specific feature from a particular image. How does a convolutional filter works? It takes, let's say, a sort of dot product between parts of my signal and the filter, and then with this I get a weighted sum of this image. Of course, the characteristic is that this filter passes through all the signal progressively, as it was already anticipated. What is, of course, important in a neural network is that I am learning the convolution weights, so the entity of the different weights in the filter from the data and not inferring them a priori. And of course, I can use a pack of them because I will not have a single set of filters for a single layer of the convolutional network, but many filters that I can decide in order to extract as many features that I wish with as many degree of complexity that I'm interested in. And Tom was telling, of course, if I am using just a linear transformation and having something that can map in a way just a linear convolution, well, that can map a linear convolution to a linear convolved image or a linearly convolved spectrum, but I can be nonlinear. Because this is a soft nonlinearity, but it's the one that is mostly used nowadays, or a restricted linear unit that is actually linear only for a part of the value that is handed out by the convolutional filter and zero elsewhere. So it's a piecewise linear transformation, but of course I could use even more nonlinear transformation of the output of the convolutional layer if wished. Pooling is the other option that it was reported. Pooling is very simple because it just summarizes a part of the signal that but it's not reactive anyway. A part of the signal summarized and compressed in a single number. Here I'm using pooling to summarize this part, a 2x2 rectangle of the image, into a single number and so on. And I can do a sum, a maximum, or other, or the max, yes, sum, maximum, as the possibilities, and in many words, maximum, max pooling, which has been shown to work the best. Okay. As an end user, what is the advantage of doing compression or pooling? First of all, of course, to compress the data. That is always good because it gives us at each stage a lower number of adjustable parameters, so a lower possibility of overfitting. Also, in a way, especially when dealing with images, but also with spectra, since I am locally averaging, or anyway, I am locally compressing the signal, I make the signal invariant to small distortion, small shifts, or small transformation that actually makes our model more robust towards variation in the original signal. And of course, if the aim when it was designed is for object recognition, for instance, in hyperspectral imaging, then it makes a representation of our data, of our image that, and of our classes that we want to detect, that is insensitive in the position with respect to the position of the objects within the image itself. And this is just a summary for both for two-dimensional or one-dimensional signal, how a convolutional network would be. I finish this let's say, troubled presentation with one that was another aspect that I think it's important or can be, let's say, withdrawn or borrowed from deep learning with, let's say, in the context of spectroscopy. That is the concept of data augmentation. Data augmentation per se also is not something that is proper of neural networks or of deep learning. But of course, deep learning provided additional way of doing data augmentation. First of all, why should we need data augmentation? So, first of all, data augmentation means, of course, getting more data in our data set with respect to the one that we are able to produce by as real data. So, of course, because it allows us to train the model using a larger and more varied data set, and this would hopefully lead to a better generalization ability of our model, because our model would be trained on a wider range of cases. First, as a simplest level of data augmentation, we can have our own data just with noise added or with some random permutation of the elements of our data set. We can have approaches that are non-deep learning based and approaches that are deep learning based. I will just very briefly draw to these two and then conclude. Yeah. But I would take probably less. So this is an example of non-deep learning based data augmentation. The idea here was to use, in this case, mid-infrared data to classify vegetable oils collected possibly across multiple instruments in different laboratories. So in this case, the data augmentation was used in a way to try to enhance robustness with respect to model transferability. And this was made in a chemical way. So first of all, producing mixtures of samples of different grades or collected by different instruments, of samples collected by the same instrument after different conditions as the first possibilities of increasing the data. Another second part was to induce multiplicative and additive noise to the data. So actually to induce, to do the inverse of an MSC, to produce a multiplicative effect, doing some shift and eventually adding some noise. And in this case, of course, by this kind of data augmentation, the authors were able to increase by some 15% the classification ability of data trained on an instrument and transferred to the others. Data augmentation, deep learning base is, at least for the application, especially in the near-infrared and spectroscopic domain, achieved to a network architecture called Generative Adversarial Network, or GAN. The idea of this network is to have some real data that we know that they are real, and to generate data with a second neural network architecture. So normally one would start with a random vector, and as you see, unfortunately, not all of you can understand Italian, but the t-shirt that I'm wearing tells that a random answer will be always granted. So we start with random noise. With this, we generate a signal that we suppose to be compatible with the real one. And we have the real signal and the generated signal. They are subject to the set of the neural network that is called the discriminator. So we have a generator and we have a discriminator. And the idea that probably in the beginning, we will be able to discriminate between the true signal and the false. But ideally, at the end of the training procedure, we will end up with a random signal, well, with the generated signal that is subjected to the discriminator, and ideally we have equally probability of being random or true. So that would be the way we would be stopping. And here there are some examples. Most applications are in the domain of classification, where we will normally train the different classes separately to have signals compatible with one class and the other. but there are also possibilities where we can have what is called a semi-supervised GAN, where actually we have all together in the discriminator both the classification, the real classification network, so the one that would be that we would be using for classifying, for instance, here for background, crop, and width, together with the discriminator network used for discriminating between the fake and the real images. And what about regression? Of course, for regression, for instance, also to generate a reasonable Y connected to the X, one possibilities, and this was from one data that was used, was in the domain of NIR spectral imaging. The authors, yes. So the authors were range scaling the X and the Y, concatenating them, and then subjecting this signal made of X concatenated X and Y to the GAN in order to get the final spectra and corresponding reference value. And you see how for one of the input, how across the training gap of the GAN the signal moves from completely random to taking the shape of a spectrum up to the very final signal. Just to conclude, so if we want to compare in the context of data augmentation, what could be the advantages of the disadvantages of the different method? Of course, the non-deep learning based methods are easy to implement and quick to apply. They create some variability, but they don't create real, how it's called, semantic variability. So we are not exploring really outside the data that we have in our training set. And of course, they can be highly sensitive to noise and outliers. They can work probably a little better when there is a higher class unbalancing, however. GAN-based method, they generate data that are realistic. They have real variability, and they can also learn complex data distribution, but of course they are more intensive in terms of time and computational resource. It may not be easy to train them, and of course it may not be easy to actually really evaluate how the generated data are. So are they really good data or not? And the same more or less extend even with more difficulty to the SGAN methods that have been shown as a very quickly before. So thanks a lot. Okay.